So now we're starting the AGS series, right? So we finished with the booster practical series, and now we have the AGS series. So I think everybody's arrived. I think we're ready to begin. Let's try it.
So like we said, today we're going to talk about booster extraction and AGS injection, which is sort of one process. I'll try to leave off where, I'll try to pick up where Travis left off the booster acceleration talk, which is just at the end of the acceleration ramp before we're ready to extract beam from the booster.
You can hit the space bar, the arrows left and right.
It's not selected, just click in the window somewhere. There you go.
Right, so we'll do what we do, what we've been doing throughout the series is just talk about the process a little bit, look at some of the tools that are available to you, and then talk about diagnostics and troubleshooting. Common problems, things to look for when booster extraction efficiency or AGS injection efficiency are not as good as they have been previously. Less concern is the initial setup, and I think at this point you guys know that there's a practical exam that goes through the point as well. So booster extraction, I think we can talk about in four major parts. One is before we left the booster, there's a booster to AGS synchro process. This is the first time in the series that we've been talking about synchro, so we'll talk a little bit about synchro in general and then specifically for booster to AGS. That prepares the beam longitudinally, right? The frequency and phase of the bunch as it leaves the booster has to be correct to land in the AGS bucket. This isn't a concern for booster injection or NSRL extraction because the RF is off during those processes initially. So there are some different concerns with booster AGS extraction. Then what I call booster extraction proper, which is the magnetic process that kicks the circulating beam out of the booster acceptance and into the booster to AGS transfer line, BTA line transfer, which is largely geography, and delivers the beam to the AGS, and then AGS injection, which is a similar process to booster extraction in reverse. So we'll just talk about each of these in series. So this is an overview picture just to orient yourself, right? Tandem and then the booster, and this is just an inset of the booster and the AGS transfer line. So this is the booster ring, this is the AGS ring, this is the booster man gate, right, or the booster plug door. This is where you walk into the booster, right? This here is where you walk into the booster. Right here is the extraction septum. So typically there's a big, there are all the shielding blocks there, which I suppose, I haven't been in, but I suppose they're moved out now for the moment. So now would actually be a good time to get a look because usually it just looks like a concrete shack. And here, this is the booster to AGS labyrinth, right? This is one of the last things that you sweep out in the booster sweep, right? This is the direction you walk in the booster sweep. And then this here is the AGS, and the AGS injection area is down here. And, you know, we'll zoom in on each of those parts in turn. So this is the booster AGS transfer line. This is just another view. This is these are the booster main magnets. So the extraction septum is in here. Then we go out, DH2 and 3, right, the critical devices for booster extraction for the AGS. Just to be crystal clear, right, this break here is just so that everything fits on the page, right? There aren't like wicked bad dog legs all around. And this break is longer than it looks, right? There's a lot of, the entire length of the BTA labyrinth essentially fits in there. And there are no magnets. Okay, so that's the very bird's eye geography lesson. So we talked about for NSRL extraction that there is no sort of master event. There's no event that comes out and from which all the extraction equipment is timed, right? Everything is just functions from T0 that we line up. For fast extraction to the AGS, that's the other thing, right? So booster to AGS extraction, booster fast extraction, those are synonymous sort of loose terms that used to describe the same process. So this is really run by two, there are in fact these master triggers. So when these triggers come out, everything that has to do with extraction is really a delay from these two triggers. So one is this synchro start trigger. The sync start trigger controls all of the RF gymnastics that we have to do, the synchro process. And this extraction start trigger is the trigger from which all of the magnetic equipment is delayed. Without these events, it doesn't, extraction won't happen properly. In fact, the extraction equipment won't fire without extraction start. You might get out without synchro start, but it's going to be pretty ugly. And probably not. So these would have to be enabled and configured properly before you ever got out of the booster. And just to give you an overview of the time scales that we're talking about, synchro begins about 15 milliseconds, so that's real time before the beam is actually kicked out of the booster. Extraction start happens about 5 milliseconds So these are real times, but you'll notice that these two are Gauss times. Why would we use Gauss times as opposed to real times for booster extraction? Why would we care? So for instance, the AGS extraction is real time. Why do I care less in the AGS than I do in the booster? The magnet isn't ramping, and so I can move extraction in time by quite a bit without changing necessarily underlying parameters. But in the booster, the field is ramping at this point, right? Which is a critical difference and makes the synchro process very different from what it is in the AGS actually. So it's important to realize that things are changing out from underneath you during the time, so that's why we use Gauss triggers rather than real-time triggers. It also means that the value of this trigger determines the energy at which you extract, right? The energy at AGS injection will be different based on what you set the Gauss trigger, the extraction start trigger to be. This is the pet page for all this, booster extraction timers. Here's things start, and here's extraction start. There are fine delays for the extraction equipment up here. Does anybody know what this is, by the way? It's GS trig up, the generic Gauss trigger. So you can set that to whatever you like. It's usually used to trigger scopes at an arbitrary time in the cycle if you don't want to use real time, which is nice because in as much as the main magnet is reproducible, real time and Gauss time should follow. But if you try to trigger extraction, for instance, on real time, you say, well, it just happens so many milliseconds after T0, you'll find that it jitters around. And digitally, right, because it comes out on a Gauss clock count, right, and the Gauss clock is discrete. And so if you slip one Gauss clock count, you can slip a finite number of milliseconds, right? It's not a continuous relationship. Right, so I want to talk a little bit about what synchro is meant to do, why we need synchro in the first place, where we didn't in previous transfer processes. So in this case, right, the beam is bunched already. Right, when it comes from the tandem or the linac, it's this long stream, right? That's more than a turn. So we have to do something other. We cannot just capture it in buckets because it's longer than buckets. But here it will come from the booster bunch for the same reason, right? It has to be bunched at extraction because we're ramping. If it weren't bunched, it wouldn't even be there. So we'd like to keep it that way. So the bunch has to stay a bunch and land directly in an AGS bucket. So to continue with right, Travis's picture of things, in the booster, right, and for booster injection, we sort of didn't care because the beam was everywhere, right? At booster injection, it would look this, and then we just put the buckets anywhere. So the timing didn't matter because the beam was everywhere in time, right? Sorry. So this is energy or momentum relative to the synchronous particle, right? That's this guy, the guy who arrives at the RF at the right time and the right energy all the time. And this is delta T, time of arrival relative to the synchronous particle. Right, so I'm comparing AGS injection to booster injection at the moment, right? So this is what booster injection looks like, right? The beam comes in from tandem in a ribbon, and we just capture wherever, right? We turn the booster RF on very low, and then we do this adiabatic increase and capture the beam. And the phase is determined then by the RF. The beam is everywhere, and so the phase is determined by the RF. We can capture anywhere we want. In this case, though, we're going to take this bunch, which has a non-infinite time delay, right? It has a finite time spread. And we're going to inject it into the AGS. So this is AGS injection on the other hand, right? The RF is on already. So there exists a bucket already, right? And so it's important at what time you arrive in the AGS, when it wasn't so much at what time you arrive in the booster. Because if you extract from the booster at an arbitrary time and land in the AGS at an arbitrary time relative to the synchronous guy, right? If you land here, you're done, right? You're going to move along the separatrix, and this guy will be sponged and blown out. Similarly, if you land inside, but off in time or at the wrong energy, you land somewhere around here, and then this filamentation process that Travis talked about kicks in. And so a beam with an emittance that looks like this initially will slowly begin to sort of smear out over the course of many turns, and sooner or later you occupy this whole area, right? And so where before you had a beam that was this big, you now have a beam that's this big, right? That's emittance blowout from injection mismatch. Right? This is the same thing we do in RIC. In RIC, it's a little bit easier to see, right? This is the applied P, applied B situation, longitudinal matching. So it's become important here to get both of these parameters correct, right? This is the synchronous particle. You have to get the energy correct and the time correct in order to prevent this emittance blowout, which is a concern now that wasn't there before because we weren't injecting much beam. And all of this synchro does is make sure that this happens correctly, right? It corrects the phase of the upstream system, right? We have these master-slave configurations. So typically the accepting accelerator, the downstream accelerator, is what we call the master. So the parameters are completely dictated by that. We set them, and then the upstream or slave accelerator has to move to match those parameters, right? In principle, you could do it the other way or something like that, but in our case, the upstream accelerator that moves to match. So we're going to change the booster parameters to match whatever is going on in the AGS. So if the phase correct, which is just what I showed you, right? You have to leave a bucket in the booster and arrive in the center of the bucket in the AGS, and it locks the revolution frequencies to, we usually say, it's sort of loosely, we say match. The frequencies aren't equal, right? The revolution frequencies can't be equal. Why couldn't they be equal? The difference is doing all of this at a constant energy, they've stopped accelerating and going to transfer. So all this happens at the same energy, and therefore, so we say match all the time, but that's kind of loose. They have to be rationally related by the ratio of the circumferences. Because otherwise, even if you got the phase right for the first bunch, the frequencies weren't related like this, you would slip every turn. And in fact, slip bunch to bunch. How close is it to 4 to 1? I have no idea. To within the precision of the measurements? I don't know. It's not 3 to 1, right? I mean, it's going to be close, is all. A 10% problem in the RF frequency and you're done, right? So 4 versus 4.1, which is roughly 10%, right? 4.4 would be 10%. You never get out, right? That's huge. That's massive. Right, so rationally related, so 4 to 1 in the case of the RIC to the AGS, it's 19/4 is the ratio of the circumferences, right? Right, I'm going to great pains to not use loose things like match, which give you the wrong impression, I think. So in the booster, right, we've been accelerating on frequency and phase loops. So that's how we've gotten to this point in the cycle, right? So frequency, time, right? So just to review what Travis was talking about, what determines the frequency here? So this is frequency in the booster. So what determines the booster RF frequency at booster injection? Right, so this is booster beam control. So this is just a set point. And then at some point, we need to accelerate. And so what determines the frequency here? Right, so, and, right, this is Travis's 5-part, right? So it's the RF program plus the frequency and phase loops, right?
Also, don't forget though, at injection, you can vary the injection frequency by changing the radial steering pump. The first and the third term in that equation I gave you. The booster being controlled plus the radial steering. So if you want to scan the injection frequency, you can do it with radial steering rather than having to keep going into that awful program and changing the parameters.
That awful program that does but the one thing.
Right, but it's not even a nice way to do it. You change it, you say okay, and that whole window disappears.
Yeah.
Then you have to do parameter injection frequency again and change it. That's not a nice way to walk out.
So at some point, we want to get off the RF program in the frequency loops, and the frequency needs to start doing something to match the AGS, right? Again, like instantly go to match, right? And so it's at this point that we hand over the frequency control from all the things that we just talked about to synchro. Booster synchro is more complicated than AGS synchro. At this point in the AGS, you could say feedback loops and go do it. The problem here is that, in fact, we are still revving. So at this point in the cycle, rather than go to feedback loops, this sync start trigger comes out, and the frequency control is handed over to something called the synchro table, which is something I've never actually seen in my life. So just to say that. So it's a pre-recorded table of frequency versus time, right? We set up booster extraction without synchro on, right? And the key part of we does that typically, right? And the booster low-level RF can record what the RF is doing between synchro start, well, for the last 15 milliseconds before, 15 or 20 milliseconds before extraction actually happens. So when we're setting up this way, we can set up the frequency based on the loops and the radial steering and all of that, on all the knobs we had for acceleration, right? We can match the AGS frequency using all of the knobs that we had because we haven't turned the synchro system on yet, right? Until we get the frequency correct. The phase, however, is going to be completely random, right? We haven't done anything to correct the phase. So you can extract, you can circulate in the AGS, but whether you land in a bucket is anybody's guess. You might as well set up with the RF off in the AGS. So the booster low-level RF can then record what it's been doing for the last 15 milliseconds of every cycle. And we can play that back. And so what happens, so we keep, say, the synchro table or the low-level RF, table, say the synchro table, you turn synchro start on, and then rather than follow the RF program and the feedback loops, it now follows that table that was loaded down to the RF. And presumably then, you're set up such that the frequency at extraction time is correct to match to the AGS. As I said, the phase we still have done nothing about, right? That is taken care of with a feedback loop. So there's another trigger called sync loop start, not the most distinct name. So we've been on sync start, right? The frequency has been following the frequency table, and then at sync loop start, the frequency is held fixed. So the phase relationship is now locked, right? Because the frequencies were made to be, like I said, commensurate or matched. So the phase relationship is locked between the bucket, and then, but non-zero, right? It's some arbitrary value between negative 180 degrees and positive 180 degrees, and then a feedback circuit kicks in and ramps this down to zero. So now the frequency is correct, phase is correct, and the RF can then generate a trigger for the magnetic extraction from this. That won't make sense. So we are longitudinally set up to leave a booster bucket, land in an AGS bucket. And our energy will be matched because we selected the extraction frequency, and the phase will be matched because of this, the synchro table plus the ramp down circuit that ramps the phase that comes down to zero. All the while, the AGS has been sending a reference signal of its own RF waveform, right? And the low level RF compares the two, and if there's any beat between the two, that implies the frequencies aren't the same, right? If you sum them, you get a beat frequency. That implies the frequencies aren't the same because of phase difference. That's how the measurement happens. But the point here is that the synchro table gets the frequency right, and the ramp down circuit gets the phase right. And like I said, it's complicated, and we can talk more about it.
Are we talking about when a beam just leaves booster, or at the beginning of the jazz? Or
So right, we haven't at all left the booster yet. None of that has even been thought of.
Okay.
Right. This all starts happening about 15 milliseconds before extraction, and then for the last 5 milliseconds, right, the magnetic stuff starts to is triggered, and part of this process is overlapping, but this has started beforehand.
I think loop start is just an independent.
Sorry, good. This is a delay. Right. This is a delay from sync start.
Presumably, when you get that one, the radius, to get this phase shifting, you actually have to pull the radius by one watch, one would see the radius pull one way or another to allow the phase to walk.
There would have to be a transient, right?
Yeah.
And
You
right.
could land at the same radius that you started at.
Oh yeah.
Right, but you would have to speed up or slow down to sort of catch up with the other, right?
And that's the thing, if you look at a booster cycle and you see a loss at synchro time, that's because the radius is far off, and when you do this transient, you walk somewhere that you lose beam. So if you see this loss at the end of synchro time, that's when you can adjust. You talk about BTA phase in the next slide? Okay. So you can adjust a knob that lets you say where zero is. So right now this ramp down circuit takes the booster phase to match the AGS. But there's still, you can tune what the zero is, so you can make an adjustment with what I'm talking about.
I don't know that it's on the next slide, so this
Okay.
is a good enough place.
BTA phase is the knob that lets you tweak where the zero is. So just because the booster RF thinks that it now matched perfectly the AGS, things drift over time. You can change where it's going to in phase by changing the BTA phase knob.
Give us a sense of where that is in path.
It's in an awful place right now. I think you have the path, don't you?
It's right, but I think it's in like diagnostic or something. So it's late.
Right. Well, you can get to it in.
Extraction radius?
No. It used to be there, and it's not there anymore. There's like a dead thing. It's in one of the low-level VO2 channels.
No. The new, I think you're right.
Oh,
Booster extraction
booster
ring. The new parameter.
Oh,
is
right,
there.
I updated that, right. So
Yeah.
it's booster extraction ring. There will be an ADO page that comes up that gives you BTA phase for every user.
Remind me what in degrees.
In degrees, right.
Instead of volts.
Right. Yeah, did nothing for me.
So remind me. Yep.
The pre-recorded table,
Mm-hmm.
that's done 15 milliseconds before the end of the cycle, or that's done
Before you intend to extract, right.
Right now, it's actually 10. We switched a couple
It's
years ago to 10, but it has to be either 5, 10, or 15, just because of the length of the memory block and the scope that's used to create the table.
Right, so you can only record so much frequency table.
So at the end of every cycle, a new table is created.
No.
Oh.
You save it once, when you're happy with the setup, it's like replay. And then we play that function every time. So in as much as the booster main magnet is totally reproducible from that for 15 milliseconds before extraction, 10 milliseconds before extraction every time, this works just great. In as much as it's totally reproducible for the 10 milliseconds before extraction.
And that's why after a month or two, Keith will say, he'll look at the booster late number to AGS early number, and he'll say that it just keeps going down. He'll make a new synchro table, because things have drifted enough that he needs to make a new one.
Okay, so now I'll move on to the transverse portion of booster extraction. So are we cool with the longitudinal part for now, or are there more questions?
Wait, yeah, you said you were gonna tell me how you can change the AGS injection energy. I mean, if you change those two triggers together to offset each other, then you've done nothing, right? I mean, still you have to change how high the magnet field ramp, the booster magnet field ramp.
No, the magnet field doesn't peak until well after all this stuff. So by changing the Gauss clock triggers together, if you move sync start and extraction start GT together by the same amount in Gauss, you will change the energy that you're extracting at. Not necessarily now going to match the AGS one. The synchro table will be wrong, yes. As soon as you move sync start GT, the synchro table is now wrong.
Right, so why would you ever move sync start?
You would not.
You would move
You would
if
never
I wanted
move.
to change the extraction, I would move extraction start.
You would move extraction
So I
start.
move farther up or down. I could move farther up on the synchro table, and then fire the extraction equipment.
Oh yeah, that's true.
That's what I'm saying.
I don't know how long the synchro table lasts.
Past extraction start, right? Okay, so if you fall off the end of the table, you're
Right,
toast.
then.
All right.
Yeah.
But I'm not thinking of changing it by Jeb, right? I mean, I'm small.
I don't know, because we never do that. Once you set it up in the beginning, that's it. You set it up the first time without the synchro table. You move the extraction start GT until you get the energy to match the AGS energy, and then you do a synchro table, and then you don't have to tune it anymore.
I just have a question for the lecturers. So is there, are there though any circumstances under which I would care to move the energy of extraction? I mean, that seems, at some level, that's somewhat irrelevant, right? Because what I really want to do is I just want to continue the process of extraction, and I'm going to constantly be changing the energy. I just have to change it between two machines. But are there circumstances under which I would care about where the energy is, what energy I'm extracting in?
Do I ever tune extraction energy? No. You will tune you'll tune the phase, but that gets you close enough. I can't think of any time I've ever changed it, unless we have a new setup. And if we have a new setup, we're off synchro, and we're doing all this from scratch anyway.
And you would pick the extraction, you would set extraction start to get the energy of the AGS, right?
So one more question then. What dictates the energy at which I start accelerating in the AGS? What energy is appropriate to choose to start this process of extracting from the booster and accelerating in the AGS?
So depending on what species, the polarized proton transfer energy is much more tightly constrained than, for instance, heavy ion, because the locations of spin resonances is energy dependent, right? So you want to transfer as far from a resonance as possible. So you're stuck between two resonances. We'll get very far afield if we start talking about polarized protons and stuff. But the point is that the polarized proton is heavily dictated to be as far as possible from spin resonances. For heavy ions, I think you accelerate as much as you can in the booster, and the constraints there are pulse power and things like that, right?
And the harmonics,
the
the
frequency
the
range
RF
in
can get to.
the booster they are, and the booster and the AGS, right?
Yeah, you want to keep it in the booster as long as you can, because the vacuum is much higher in the booster.
That's kind of what the booster's there for heavy ions. So now, once you're synced up, the RF generates a trigger for the kicker. for these kickers. So for the magnetic equipment, right? So to get out of the booster, just like to get into and out of the AGS actually. So it's sort of important to get the general scheme here right, because this, you'll see the theme repeated for the next few talks, right? There's a closed orbit bump, which moves you to the outside of the machine, so that needs to be extracted. There's a kicker and a septum. The septum is just like the D6 septum sitting on the outside of the machine. Oh, I had a schematic. It's on the outside of the machine, so we move the closed orbit as close as possible, and there's a kicker just upstream of the septum that moves you across the septum into the bending field and then down the line. And I'll show you. Like I said, AGS injection looks like booster extraction in reverse, and then AGS extraction looks much like booster extraction. So this is the bird's eye view of the booster, right? Each one of these is each box here is a main magnet, 6 super periods, 6 magnets per super period. Here's the injection area in C, and then over here is what we're talking about now, is the extraction area. So the kicker that I was talking about is here, the F3 kicker, and the septum is here, right, at F6. I don't know, it's a curious thing. I didn't notice this until I was here for a bunch. Everything interesting in the boosters, the 3s and 6s. You know that? I mean, the RF cavities, A3, B3, A6, E6, E3, P6, F3, F6. It's all 3s and 6s. So there are missing dipoles there, right? This is a missing dipole lattice. So they're evenly spaced, except at all the 3s and 6s, there's a dipole missing. So you sort of can't get the number wrong for half these things. Anyway, well, I guess you can get the number wrong for exactly half these. So like I said, there are backleg windings, just like for NSRL extraction, to move the closed orbit closer to the extraction septum. In this case, they're around F2, F4, F7, A1, and there's a better picture of it, giving the lay of the land here. And that's supposed to be, that bump should be centered around the F6 region. Controls for that are in PET, and I'll show the PET pages. It's important, so it's important at this point to start distinguishing timescales, right? We sometimes call this a slow bump. The bumps are on the scale of milliseconds, right? The kicker's on the scale of microseconds. They're, 1,000 times shorter, right? So when you put these things up on a scope, you have to expect that you're going to see drastically different things at different timescales. And in fact, at large enough timescales, you can miss the kicker altogether, right? You will tell yourself that the kicker is not firing because the resolution of the scope doesn't even see it if you look from far enough away. So it's important not to fool yourself, right? You can check the bumps, and then you do have to change the scope setup to check other things. Right, so both the amplitude and the time that they fire relative, right? All of this is relative to booster extraction start. Can all be set in PET. So this is a view of the extraction bumps. So they don't have functions. They don't have functions like the NSRL extraction bumps. There is a voltage that we put on them and a discharge time. And you're at the mercy of the power supply circuit to give you the waveform. So this is just discharging a voltage through an inductance and boom, you get this waveform. So you'll note the time scale, right? 2 milliseconds per division. So they're about 4 milliseconds at the base. 2 milliseconds rise time, you might say. So I have a question. So if booster extraction efficiency is terrible and I put this up on a scope, I want to blame F4. Like, is that fair? Can I blame F4 for poor booster extraction at this point? I can probably read the label, right? F2, F4, 7, A1. So they're in order. So I'm trying to make
in general, it looks a bit ragged, but there could be a lot of other factors that are ruining booster extraction. Instead of just looking at F1 and showing me, oh, it's definitely that because it looks a bit crappy.
Right, so that's my point, right? It's ratty compared to the other ones. The other ones are these nice tight lines, and this has all this noise on it. So this is, I'm trying to drive home the point that it is important to know what things look like when things are running well. Because if you have no idea, then you will find scope traces like this everywhere. They look awful. The AGS extraction bumps always look like the problem because they look like a problem. They're terribly hairy, so I was kind of glad that one of them was worse than the others, right? This probably always looks like this. It was almost certainly not the problem, right? This is probably a muck issue, some piece of cable somewhere or something like this.
So what's the signature, if you pose that, what's the signature of a problem? What would change if I were to encounter a problem?
Okay, good. So typical to these guys is a gross amplitude change, right? So these guys have resistors in them. The injection pumps used to be worse for this. But there are times when one of these amplitudes will just be way off. There will be a problem with the power supply, and it will fire. But the amplitude of the bump of an individual, the current from it, these are all currents, incidentally. Because you can get the voltages too, and that will mess you up if you don't know what you're looking at, right? The amplitudes will be drastically different, usually much lower. And so you can fool yourself with a scope setup, right? You say they should all be equal, and then you go crank, 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 crank. You're just trying the gains on every one of them. And it's very easy in a fast scope setup where you're not really, and then you say, no, that looks beautiful. It looks just like the reference picture.
Notice, I'm just going to point this out, notice though that there are different voltage settings here.
Yeah.
So you just, the point is, you have to be careful. You just have to know exactly what you're doing and not just sort of, you know, go to sleep.
No, they shouldn't.
There are
be.
2 big ones and 2 small ones.
Right.
Don't ask me which one. So right.
So I also want to ask that question, like, should we have it set up so that way they're all one voltage on the scope? Like, say,
That would be
small
better.
or 2?
That would be better. I mean, it at least works as a standard, right? Then we know what they look like.
More importantly, you should have it set up how, I mean, if I pull up these pictures, I have no idea intrinsically what I do, but you don't. How do you know? How do you know what they should look like?
Look at them when they're healthy.
Right.
Look at a reference.
But, right, you have to look at the reference picture. The important thing is that the reference picture looks like the current scope picture. So you adjust the scope. Hopefully whoever took the reference picture had all the same voltages, I would hope. But if they don't, make sure that your scope looks like the reference picture setup, and then you can compare things. Because you can even see F4, for some reason, always leans to the right. F2, ideally we want to extract from the peak, but you can see that we're always going to be a little off the peak of F4. It's something about power supply, I don't know what, but always look at the reference picture.
Guys, and let me just throw in something too, is you'll remember before I mentioned practicing. This is I think, personally, I think this is exactly the kind of thing that you can practice, is you set this up when it's working properly and you sort of burn into your mind, this is what things look like when things are working, and you try to understand the relationship, the timing relationships here. So that you're not thrown by this. This is, again, this is a nice picture, actually. I like this picture because it tells you a lot of things that you should be learning and tells you how to avoid the things that you shouldn't be, like the inconsistent amplitudes here. But it does tell you what the time scale is that you should be looking at. This is 2 milliseconds or whatever per division. So just, this is exactly what I mean when I say practice. And everybody's been making the same point. Just look at things when things are working so you understand what you're looking at, especially when things are not.
We can still extract without aspect, right? We just need to crank up other 3 and then as
Without
long as you don't
without-
break it. I'm sorry?
You mean F4? Well,
I mean, other 3. You have
Yeah.
4
Right,
bumps
can you,
there, right?
can you tune up with 3
Yes,
extraction modes?
yes.
Probably.
Have you ever tried?
I have never personally tried.
As long as we don't
Sounded
break
fun,
it,
though.
free, right?
Hey, can you play the plane with 1 engine, or do you need 2?
why would you try?
How about, like, I think anything can happen if you lose at 4 and then you want to extract. I
Okay, the
mean,
problem though is it's not so much a problem of getting the beam to the bump, or getting the beam to the to the kicker. It's also, these guys create an orbit distortion and have to close it. So for 2 milliseconds, the beam is on this orbit. So if you have one of these guys off and the orbit's not closed, you might get out to F3, but then it's doing this around the machine. You'll probably lose it as they ramp up anyway.
I mean,
Right, so she's saying you could make a 3 bump, right? You could try it,
Yeah,
and
you could, okay.
yeah, you can increase the amplitude of
with the state of booster
right?
orbit control, good luck, is what I would say, right? Like,
I don't know. I don't know why you would ever want to. I wouldn't try. I would fix it first because,
Right.
I mean, for most of our programs, we're so worried about admittance that you're going to go into the AGS all crazy and stuff. So you should fix the power supply.
If they tell you the repair is going to take 2 hours and you have nothing better to do,
Right,
by
then
all means, go for it.
Except when they fix one, they're going to take down all 4.
Yeah, right.
So,
Let's say, okay, let's say after the maintenance, right, you have problem with F4, but you want to see whether with the 3 bumps you already have, whether you can extract to rate, for example, but the maintenance people or power supply people gonna use like 3 hours, or they need to wait, you know, a period of time to fix that power supply. So So you just really want to see whether you can interact. I mean, that time.
It's possible, but I
Yeah,
think you're gonna spend
that's
more
why I
time,
was-
and if you eventually do get it, it's gonna take you so long that they're gonna have the thing fixed, and you're gonna have to unload everything and go back to where you were.
It's not trivial to
Right, I
to
mean, the
change.
machine is designed to run the way it was designed to run.
But how are those currents set though? Because it's not an orbit, 'cause it's not
It's
a
an amplitude.
calculated pump. It's
It doesn't.
discharge.
The power supplies are cat banks, you're running them through a certain amount of, through an inductor, and you just fire the
It's
cat
just
bank.
for value, right?
Yes.
Right, so
So
we do it the same way we do
what
everything else.
physicist told you what values those should be?
Who's the LP for the booster? No.
No.
The LP for the booster? Come on.
No, I'm saying, does somebody say what we should set them to, or does Keith just tune them? Because
Yes, both, right. We start with the values that were calculated on some desktop somewhere, we put them in, the beam dies, and then Keith sits there and tunes every knob in creation, right? It's the same way we do everything else, but you're close with a calculated 4 bump, and then Keith does his worst, right? And then the efficiency is 10 times better than it was with the theoretical value.
Right. And it used to actually be calculated by the program. Booster orbit control used to actually do it
Right.
for you, and now we control it directly.
So is that in Gardner notes, if we want to, like, reset?
No, this is the
Like,
kind of
how
thing
we-
we'd love from an archive
I mean,
at
those
this
things
point,
have been
right?
changed so many times, probably.
No,
What are the relative values? How are we gonna know where the relative values are?
Archives.
Use archives.
Right, if we got ourselves into a place where like scaling wouldn't work and it was totally, right, we were so far, I can't imagine a scenario, but we were so far from any previously run scenario that we would calculate the bumps just with, ciphers. You just go through and calculate position and angle of the septum, put them in, and when it doesn't work, you tweak from there, but you need a starting point. Right, that's the point. If F4 went to lunge, you would be far from the right settings for a 3 bump. And little tweaks individually on every one aren't going to get you there, right? You would really have to start over again.
You have to know a lot about, you have to know the machine, yeah, you have to know the model, and so that's why it's not a trivial thing to do. Could be done, but it would be difficult.
Okay. So, for instance, this is a model, this is from like an ancient tech note. This is a model orbit distortion from the extraction bump, right, as calculated, right? This would be the ideal value. So this is F2, F4, F7, A1. The septum is this S here, so it's meant to peak around the septum. The F3 peaks here. So this is what the beam sees on its last trip, its last turn in the booster, right?
Axes. The axes for the graph.
Sorry, so this is the S coordinate, so in meters from some arbitrary place, the beginning of the F super period, I suppose. And these are millimeters. So this is a 40 millimeter bump, right? No chump change, no chump change bump. But the septum is 76 millimeters from the center line.
Right, so this is the last many turns the beam sees, right? This is the orbit bump.
Yeah, right.
So when you get to that first peak, and you're ready, it's time to extract, F3 is going to give an even bigger kick, which will change that end trajectory and kick you out of the machine. Like, this is what the beam does going around the machine when it gets near F, with the bumps on. When it fires, it's going to get a big, you can just sketch
Right.
it.
So, I mean, the edge of the septum is double this, right?
Yeah, right,
Double
right,
80
right.
millimeters, right? So at F3, you get a kick that's, steep.
And then would it close back on itself there, or once it gets across the septum?
Once it's across the septum, right.
This is prior to.
Right, there's zero field from the septum here,
Okay.
and then after about 80 millimeters, there's strong bending that way.
So this is showing.
This
just
is the
above.
circulating beam, right, as if extraction has not yet happened, right? F3 and F6 not firing. The equilibrium orbit before extraction. These are the controls that we were talking about in PET, booster extraction ring, right, and these are the amplitude and the state control. As I said, that was the closed orbit before extraction. Beam is ultimately taken from inside the acceptance of the booster to across the septum by this space. Sorry, I have a schematic for F6, but imagine this to be the F6 septum. So this is, beam comes this way, right? This is the circulating beam, the F6 septum. So this is the septum, right? We were talking about this with P6, right? This is where the current goes around the magnet. F6 is actually in 2 parts, right? Another part here in this little gap. So the circulating beam comes through here. This is F6. Then there's bumps. Forget scale here altogether, right? And then the F3 kicker. And this actually has 4 separate magnets, all wired in series, right? And so the idea, right, is just what I showed. So the beam comes through and bumps out very gently. There's a quad right here, right? So it's allowed, the trajectory is allowed to turn around and then back onto the closed orbit, so we get as close as possible. And then this is the last, right? This is the last 2 milliseconds of beam, right? It's been slowly moving close to the septum. And then a trigger called F3A5 triggers both the extraction kicker for the booster and the injection kicker for the AGS, which we'll talk about in a minute. And then from this point on, right, you're strongly deflected right over the septum and down. And there was 0 field here, but now there's, in this case, upward bending field. So in this case, you're looking down from the top, right? And now we're down into the BCA line, okay? And like I said, this picture is pretty standard. AGS injection will look just like this, except the beam comes in this way. The closed orbit is here. This is L20 and so forth. Right? Like we were saying, ideally we extract at the peak of the extraction bump, which is very long compared to the kicker, and the kicker should fire at the top of the bump. Here we have 2 of the 4 bump components and 2 fast kickers, right? So here we have the A1 bump and the F7 bump, and you'll see their bases are very long, whereas the time scale is much smaller than it was on the other plot. The F6 septum similarly has a slightly shorter pulse time, but the F3 kicker, this pink trace, barely visible, right? On a time scale much larger than this, it would disappear altogether. So another thing to notice, and this is a common characteristic, that you see these nubs here, right? There's a little blip on each of the extraction bumps, and I think you can see them on the other ones too. You might be inclined, if you didn't know what nominal was like, to blame that too, right? There's this weird glitch every time, and that's why the orbit in BTA is all screwed up. That's kicker noise, right? That's kicker noise from, these are very close. This has a huge dBdt, and so it induces that nub on the signal there. I found this picture, which is a very nice picture, which shows you exactly what's supposed to happen at extraction by searching for the reference tag, by the way, which is, I'm advertising.
I have a question. Yeah. The nubs, I've never understood, does that actually come from, that's something that gets reflected down the pipe and gets induced onto the bump, or where did that
Is it real current in the magnet, or is it just a blip on the signal?
Right.
That's your question?
Yeah.
In some sense, it doesn't matter because the beam is gone by the time you see it, right? The beam should be gone.
Right.
But I can only imagine the signal, just because the inductance would, it's so fast that I can't imagine that it induces that on the main magnet, right? I have that in my head, but I don't know that I have any good reason for having that in my head. So this is another view. So is anyone going to tell me what's going on in this picture? What am I looking at?
The green trace.
So it happens to be the wall current monitor.
Purple trace is the F3.
Sure.
Includes
Right. So that leaves the yellow one. Right. So what species is this? and how many turns of beam do I see in the AGS? What's another conceivable answer? 2 is the right answer, right? The other answer that I was thinking of was 12, right? Because I see 12 bunches, right? With this huge, yeah. But right. So the point here is that the bunches are evenly spaced in the booster, right? So it's in fact difficult to tell how many turns you have here, right? You're tempted to say this many, right? Count P. But in fact, there are 6 bunches of gold at booster extraction on H equals 6, so every bucket is filled, and so it looks quite even. And then we extract, and so which booster cycle is this, by the way? So the booster super cycle for gold. So which cycle is it? If this is 1 and this is 5? Right, 2, right? Okay. So it's the first cycle with beam in it, not the dummy cycle. And it's 1 because there's only one group of 6, right? So I say that if you zoomed in here, you can tell yourself, oh, I get 6 turns of beam, and then something wallops the beam, right? And then you're searching for a totally different situation than you were before. So after the last cycle, this would look all even, right? Because the harmonic in the AGS for gold injection is 24, right? 6 bunches per. It has to be at least 24 because there are 6 bunches on 4 boosters.
So remember what you would see on the left side is you would see 18 spikes, the gap. Right? If you're looking at the last transfer on this, on the left side of that yellow trace, you would see 18 bunches because you've already taken 3 loads of booster beam. There'd be 18 turns and again, or 18 spikes in a gap, and then 18 spikes in a gap, and then after you get these next 6 in, it will be continuous beam on the right. There's already beam circulating around there.
Right. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6.
And then
nothing. Right. And then, well,
right. Yeah.
it's a little bit. I ran out of space, but and then on the other side, it would be evenly spaced, right? There would be no gap anymore because you've built in the last quarter of the ring. Once you're out of the booster, we can talk about booster to AGS. So the concept of out of the booster is actually pretty good. The first so there are 4 multi-wires in the BTA that are usable to look at profiles, right? They're not always plunged because they tend to do bad things to being lit, and then flow up intensity drops and things like that. So you can plunge them using profile display whenever you like, but like I said, there are no continuously monitoring multi-wires like there are at the Antro. There are other diagnostics in the tunnel, but they're not usable. So our primary diagnostic tool for BTA transport are these 4 multi-wires. The first multi-wire is multi-wire 006. The number corresponds to feet from some point on F6. So 006 is 6 feet. That far from the end of the F6 septum, right? If you're not there, you have problems in the booster, right? You can cut off a huge amount by just looking at multi-wire 6 first, right? In the same way that because there's a gap now, right? Travis had mentioned that the comfort displays, you can lop off huge sections of the machine by looking at the comfort display and saying, no, it has to be in the booster, it has to be here. There's a lot of information there that's readily available, but there's kind of a gap, right, between booster extraction, or what looks like booster extraction on the comfort display, and AGS injection, which, as measured by a current transformer, right, you have to have enough turn for the current transformer to see it. There's a rather large gap. So distinguishing this problem from booster extraction and AGS injection almost always requires scopes and multi-wires and that kind of thing. So if you are in the booster and not in the AGS, it's not at all clear at what stage you're losing it just from comfort display. So right, like I said, multi-wire, there's 6, then 60, then 125, and 166, all feed from F6, and I have the picture again, and we can look at it. But I have questions. So this is 125 and 166. I should mention, there's another one. Right? All of these guys are in the BTA. Right? The beam goes through them but once in the transfer line. There's another one called A15, which is in the AGS address system because it is in the AGS. Right? It's in the circulating beam path of the AGS. The A5 kicker is sort of the last injection element, and then A15 is a ways down. These guys have minor effects on the beam. The A15 multi-wire, if plunged, because you will go through it on every single turn, can kill the beam faster than the DCCT will even pick up the beam, right? It will look like you are not getting the AGS unless you look at, say, the wall current monitor. Because you do get many turns, just not enough to see it on the DCCT. We usually only use it for setup, just red beam around, because there are very few places in the AGS where you can see a single turn. Or if we are really, really in the soup, and we really don't know. So you can do it, you can plunge it, it's available, and I encourage you to use it. The only issue is, right, if you leave it in, and there should be an alarm on the alarm display telling you so, but if you leave it in, you can cause yourself more grief than when you started. Okay, so what species is this?
Not proton.
Not proton.
That's the better answer than
It actually is, right? I mean, in some sense, right? This could, so, how do you know that it's not proton?
Because protons wouldn't have a charge state spread, or different charge states going out.
Okay.
Which is what those little wings are on the signal.
Right, so you're talking about the lobes, right?
Yeah.
The beat guys. Okay, so we'll get to where they are, but right, these are different charge states, right? And so, do 6 and 60 look the same as this? Do they have the lobes or no? So this is gold. It happens to be gold. It could be any heavy ion, really. We don't strip protons, right?
Take other things into the AGS?
We do copper.
It's Iron Man years ago for close
Okay.
I guess it depends, the answer to that question depends on where the strip of foil is in the beam.
Right, exactly. So it happens to be between 6 and 60. So here's the,
Right, so 6, you see no lobes on it. 6 is just a single spike.
so this is the same picture again, but now we're here, right? So, like I said, multi-wire 006 can distinguish between whether you're losing it, right, just at booster extraction or later. There also happens to be a flag on F6 that they're replacing, and so it should be useful. At any rate, so the purple things, for the most part, are multi-wire. So here's 1, 2, 3, and 4. Like we said, here is the foil stripper, right? So this is a foil wheel that rotates and has several different foil holders on it. And so we can choose any number of foils. One of them is usually left blank in case we want to pass the beam through just vacuum. All species other than protons need to be stripped in the BTA as a general rule. We strip almost everything except for protons and neutrons. So gold in the booster is usually in normal operation is what charge state? 32, and then after the foil, 77. Helium-like, which is this word, it makes me insane. I think it's so goofy. It has 2 electrons left, so it is like helium, chemically, I suppose. That's just a note, right, that if this is wrong, right, the rigidities are then different by the ratio of those 2 charges, right? More than a factor of 2, 77 to 32. The line downstream of the foil is set up for a rigidity a factor of 2 higher. If the foil is wrong, lower, because the charge is higher, right, thank you. If the foil is set improperly, which is more an issue when we're mode switching, or, for instance, when we're setting up for, say, gold behind protons and protons behind gold, which may be an issue next year. If the foil gets out of sync during mode switch, you will see beam on 006, because all of this is set up just fine, and then 060, nothing. So it's important to get this right, and it's important for it not to be there for, say, protons. The rest of BTA is really matching what we see as nominal part pictures, right? So what you're looking for are missteering and drastic changes in the profile. So if you have drastic changes in the profile, we rarely tune quadrupoles for transmission efficiency. Those are sort of set and forget. If one of them trips, however, you can get a certain amount of beam down, but it would be huge and won't be matched to the AGS. So in all likelihood, transfer down the line will go bad. You can see that based on the area of the multi-wire profiles, right? That's another place where the scale can kill you. In principle, if you integrate the area under the multi-wire profiles, that's a measure of the intensity. And so if that gets grossly diminished as a function of position down the line and distorted, then you may have a quadrupole that's tripped or not following its reference, and steering is a little bit more obvious, right? And so there are some big magnets, some big benders, DH1, DH2 and 3. These are all numbered. I don't know why people at accelerators do this, right? So the big guys are numbered in sequence from the beginning of the line. So DH1, 2, and 3, which are wired in series. They're actually booster main magnets that we run way over the current we're supposed to run in them. They're 15-degree bends, and the ones in the booster, and the ones that sit in the booster bend 10 degrees. DH4 and DH5, those are the big benders, and then the small steering magnets are all labeled in feet from F6 again, right? So you have these are the yellow, the smaller yellow guys. And there are current transformers and pickups labeled here that we don't actually use for reasons I don't.
Just one note, a lot of people, actually anybody who's taken this from me, I will usually screw up the quad. If a quad is not following its reference, you'll get poor transmission. But almost all the time, if the quad is actually off, you'll see nothing. Because think about what a quad is. So a horizontally focusing quad, what's the beam doing going into it? Going into it, the beam is on its way out, right? So now the quad is off, the beam keeps going out. And the next thing it hits is a horizontally defocusing, which throws it even farther out. It's the only beam that goes dead center through that quad is going to make it down the next one. So like if you see something on 60 and nothing on 125, quads are important. If I zero QH8, you will get nothing on 125.
No, that's good. And worse than that, right? Like I said, this gap here is actually quite long. So if you're wrong going in there, right? If the beam is diverging going in there, you have a long way to go, right? And the beam just keeps getting bigger before you hit the quads that can do you any good. Sadly, 166 is much farther from the AGS injection point than 006 is from the booster extraction point. So there's a lot going on between 166, but you've eliminated a lot of the BTA, but there's still like a big bend between you and an actual AGS injection. Like I said, these are AGS main magnets. You actually pass through the outside of the coils of L20 on your way into the AGS. So like I said, this picture looks exactly like booster extraction, but in reverse. It's accomplished with the same kinds of elements. There's a closed orbit bump to get you as close as possible to the edge of the septum, a septum to bring you into the acceptance of the AGS, and then a kicker that puts you from whatever orbit you had coming in onto the closed orbit in the AGS. And all of this is important for the same reasons that we've been talking about, is this matching business, right? If you're matched to the closed orbit, the emittance growth is in principle 0, the transverse emittance growth. This is well instrumented in RIC, but you're doing essentially the same thing. When you tune the end of BTA, you're doing essentially the same thing as apply V and apply H2 in RIC injection. You're adjusting the last dipoles in the line such that you are going into the accelerator and you're matching to the circulating beam, which is hard to tell whether you're doing it right at AGS injection.
Sorry, do you have, because I took me a long time to actually get this, can you draw a picture of the whole thing, like the L20, you actually overshoot, and you're on your way back out when the A5 takes you flat?
Yeah.
Right? Just draw a picture of that orbit.
So whether I'm going to get like phase advances right, doubtful, right? So I don't know whether
Right. Yeah, but
Okay.
I just want to see the.
I don't know whether you're moving to the inside of the machine or the outside of the machine when you get to A5.
Oh, okay. I always thought you were past it and on the way back out just because you're going through. Oh, there's 20 magnets.
It's only
You're going
5
through a
AGS.
quarter. Oh, right. You might still be on the way in. I see what you're saying. All right. The important thing is though, so a kicker kicks you off the equilibrium orbit to the septum, right, on the way out of the machine. On the way into a machine, the septum pushes you toward the equilibrium orbit, but without the kicker, you're going to oscillate around it. So it's as you're crossing zero that the kicker then kicks you flat onto it. Well, right, you would overshoot and have this massive betatron oscillation, and you'd get lost somewhere else. So what Vincent's saying is, I don't know if L20 bends you in so far you go past the equilibrium orbit and you're coming back out and get kicked flat, or if you're still on your way in toward the equilibrium orbit and you get kicked flat. But either way, that's the important concept there, is that you need to get kicked flat onto it. And without the kicker, you'll just have this huge swing around the equilibrium orbit.
Got to be left.
Yeah, I would think so too. Right.
So this is a gross exaggeration of the septum, right? So this is L20, and because it's easier to do this for me from left to right, we're going to lie on our backs and look at the AGS, so the beam is going to go this way, counterclockwise, right? So the circulating beam comes in from here, right, like this, and goes over and goes around, in this case, clockwise, right? So what Travis is saying that if we did nothing and we had circulating beam in the booster, right, it has some equilibrium orbit, some orbit that it will eventually settle on, right? Which we hope, because the orbit bump that we put in is near the edge of the septum, right? So let's say, just for granted, that it's flat everywhere else, right? So we managed to correct the orbit really well. Actually, we might as well do this, right? The injection bump, let me talk about the injection bump for a moment. So the injection bump consists of backleg windings around AGS main magnets, right? And there are two. There's an angle bump and a position bump. So we control the position and the angle at the downstream end of L20. The position bump is what's called a 3/2 lambda bump. So we bump out, then in, then out, then back up again. Again, grossly distorted, right? 3/2 lambda. Lambda refers to wavelength, so this is 1 wavelength, and this is a half wavelength. So 1.5 wavelength. So here we can control the position, but not so much the angle, right? So this bump, we can scale it, we can make it go the other way. But in principle, the angle is pretty much always 0 at the peak of the bump, which we hope is near L20. The angle bump, again, backleg windings slightly differently configured, is a 1 lambda bump, and so there, right, we pass through 0-ish near the L20 septum, but we have control over this angle, right? As I change the amplitude of this bump, the angle changes, right? So we can accept beam from the BTA over some range of position and angle. It's not a fully closed bump either, so there are residuals that sort of that constrain this problem also, right? Because if you're going to lose it elsewhere, even if you're perfectly matched at the BTA, who cares? You aperture on, say the cold gate. Just random. So right, so Travis's issue, what Travis is bringing up is that A5 sits, this is L20, right? There are 20 main magnets per super period, 12 super periods. So this is the end of the L super period and the beginning of the A. So somewhere down here is the A5 kicker, right? So when you come in, you will not be perfectly matched to the AGS orbit. I'll have the incoming screen. So the incoming orbit, you hope that L20 gets you close, right? But what's going to happen is this is the closed orbit, so any mismatch causes you to oscillate around this orbit, right? So I'm going to exaggerate the oscillation. We'll make many fewer than this. But the point is that what you would like is for the angle to be non-zero and the position to be correct through A5. And then you would put an angle of this much, right, into A5. And then you would be on the closed orbit. So that's the scheme, right? You come in, the The position and angle bump are meant to get you as close as possible. The injection septum is meant to make you sort of tangent to the curve, right? You'll oscillate around this, which is what you see again in RIC, well instrumented, right? You can see the incoming orbit oscillate, the red points oscillate around the blue points. The blue point being the target orbit and the red being the first turn. And you hope that by the end of that, they match, right? And then you go around, and there's no decoherence, no transverse into this flow. Does that make sense? Right, so for initial setup, you'd be watching, like I said, if the first turn in the AGS is poorly instrumented, there are very few things that can show you where you are. We don't have first turn BPMs like in RIC. So the A15 multi-wire is available, and there are a few hardwired pickups on MCR3 where you would know, I mean, if you were around for this injection period, you know how useful those can be to know that you're even getting to the pickup and whether you have circulating beam. So all of these guys, the L20 injection and angle bump, are controlled with they're DC bumps in that they come on and they stay on for a long time, unlike the extraction bumps, the booster extraction bumps, which are these pulse guys. So they're not on for the whole cycle, so DC is a little bit loose, but they come on, they hold a flat current, and they ramp down based on a start trigger and a discharge trigger, and we can control the amplitude.
Right, the injection bumps pulse for every booster cycle. The AGS injection orbit goes up and stays near L20 for the entire injection course. So the goal, you get 4 transfers, it doesn't come back down between each transfer from the booster. It stays up for a full, almost a second.
And this is because it's all bunched already?
What's that?
This is because it's bunched in the booster, right?
It's because there's no reason to bring it back away from L20. You can leave. The reason we have to bring it back down to the booster is that we need to collapse it. Right? We push it out actually past the edge of the C3 inflector, and we have to make it collapse to get the beam in. Here, we don't actually push the orbit to the L20 septum and whack it. We just get it close. And so we can leave it there. We just leave it there while we're filling. What's that? No, this doesn't collapse at all. I mean, it stays up and then it's very slow compared to anything else. So it stays up for a second, and then it just slowly ramps back down to get you away from L20.
What's the point of bringing it together?
Or like, why do you need to get it away? Because the beam pipe is this big, and you can fit more beam if you live in the middle rather than if you live way outside.
We ramp it down before, well, not even, remarkably late in acceleration, actually. Yeah, and it's DC, so it sort of collapses on its own as the rigidity goes up. So it stays on, it comes up, so these are, if this is the AGS, right, and we have 4 booster cycles with beam, the L20 position angle bumps, right? The septum is pulsed on every side. Comes up, has this sort of trapezoidal function, right? And oh, good lord. Well, I can do it. It's actually good. Like I said, it stays on for some period into acceleration. And the bump amplitude starts decreasing here, right, as it starts to accelerate. Just because it's DC and it collapses.
Right, as the rigidity goes up, the bump for the same current has less of an effect.
Why not collapse it before you start ramping? If you have time.
That's a great question. I tried doing it one day. It didn't make a lick of difference. But I figured all the RF gymnastics we do for when we do the stuff, we would want to have as much beam pipe as possible. It didn't help at all. And Keith actually has tuned it. He's tuned all the orbit corrections to be based on when this thing collapses. So we leave it there because historically we left it there.
He probably uses it for polarized protons because the orbit is so sensitive and he wants as many now as possible. Probably makes early acceleration better with the L20. Well, I would bet on it. It's obscene, but it probably is true, right? It's an available knob and he'll use it. Right, so I mentioned most of these things. This is a nice kick in the teeth. The L20 triggers are on the booster user. So if you're transferring from booster user 1 to AGS user 4, the triggers are all booster user triggers. So the start, and discharge triggers when they turn on and when they turn off is governed by the booster timeline. The amplitudes are set on the AGS user. I have no answer for why. The question in your head is why, and I have no answer. But it is true, and it will mess you up. Right? You will convince yourself that you're doing things and you're not. The best solution I have is to always transfer from the same user to.
Is there any reason that we should leave it this way, or is there any reason why we can't change it? So that the triggers are on the AGS user, or is it just
Well, we
historically?
can't in that, I mean, it requires a hardware change. And at what point do you decide when the AGS starts and when because the A5 has to be slaved so tightly to the booster that it makes sense to use the booster trigger. Right? Same thing with L20. L20 has to kind of pulse the same. So it's a gray area. And this is how it's set up because this is how it was set up.
And it's a little bit strange because it almost doesn't matter, right? I mean, A5 has to be right exactly because it's tiny, right, in time. But these guys stay on forever. So it's a caveat that you should be aware of. Here we go. So this is the booster extraction ring page. So what we were just talking about, right? Here are the booster extraction bumps, the controls for the septa, controls for the booster extraction kicker and septum, the controls for the AGS injection septum, and the AGS injection bump. The controls are here. The state control is here. I have a feeling that that's not going to be the case for very long.
Yeah, I'm not sure what they're gonna do, they haven't turned in the final.
Luckily, these pages both come up when we hit booster extraction ring now. And so here's where BTA phase now lives, right? So this is what we were talking about before. So this is how you correct BTA synchro, and I should move this to at least have a copy over when we were talking about BTA synchro, where you adjust the phasing between the booster and the AGS. But for what we're talking about now, the state control for the booster position and angle, which have large supplies and then trim supplies, or fine adjustments. And and their amplitude control.
And also note that BTA phase is the AGS user, not booster. Because
Which
you're
at least
changing the
says-
zero level of the AGS, basically. You're changing where zero phase is by someone else.
So that's that degrees of AGS.
It's in degrees of AGS frequency, yeah. I don't know why it's at 277 and not zero, but yeah.
Right. Must be bucket
Because
frequency.
it was
Right.
really
RF. Right. RF frequency, not revolution frequency.
Right, yeah.
Just to
Yeah.
be pedantic. So this is kind of sad. I have to update this. This is I think it's Samsung. So this is a similar picture to what we were looking at before at a different time scale. This is the L20 septum, which has a similar time base. Like I said, you can think in a handful of milliseconds for most of the devices, and then for the fast kickers, F3 and A5, you think in handfuls of microseconds. And so this is a picture of reasonable booster AGS extraction. So in this case, this can only be what? Right, I mean, the same question before, what species could this be? So the time scale is grossly exaggerated, but that each peak there is a term. Okay, so as I said, the troubleshooting and diagnosis for this, you can often gain a lot from the comfort displays, but there is a gap here, right? There's a gap where we don't have eyes apart from multi-wires and real scope triggers. And the time scales are such that you can really fool yourself by looking at the booster comfort display, for instance. So if you beam in the booster, the current transformer goes to 0, and then there's nothing in the AGS, right? And there's a long way between blaming, say, AGS injection. I think that's a common thing to do, is to blame the first place where you don't see beam, as opposed to starting with the first place where you do, right? Because I know zero current transformers are scary. So these are just general thoughts about questions that should be going through your head. Right? If you're losing beam, how much are you losing beam? Right? Whether you're losing it all or is the transfer efficiency bad, and by how much? When in the acceleration cycle does the problem occur? That is critically important. the comfort displays can often tell you what phase, right, in the terms that we use to name these lectures, for instance, booster acceleration, booster extraction, AGS injection, that kind of thing. But that is the most general classification you could possibly give, right? Ultimately, you're going to want milliseconds from T0, right? Am I even making it to the extraction kicker in the booster, for instance? if all the beam is dying a millisecond beforehand, the comfort display isn't going to tell you that, right? You really need a scope. So if synchro is hosed, you're not going to be able to distinguish that from a bad F3 kick, for instance, by using comfort displays. What equipment is changing during this time? So that gets, for the booster, it's important to realize the timeline, right? You can, if synchro goes horribly wrong, you can lose the beam way before you're even thinking about the magnetic equipment, so you can eliminate all of those as a possibility. Have there been any changes? When were we last working? When was the beam last running reasonably well? Right, all of these are usual questions. Does the problem have any recognizable signatures? Right, this is about sort of run knowledge, right? Has F6 been acting up all run? That kind of thing. Also, and I didn't write here, but the time scale of the problem has it been drifting? Has booster extraction efficiency been drifting off poorly, or is it shot-to-shot jitter? Some shots are good and some shots are bad. Right, that kind of rapidly changing thing there are only two systems that move that quickly, right? RF and the pulse power. It's unlikely that a quad is coming on and shutting off and coming on and shutting off shot to shot. So tools for diagnostics. As I said, profile display is just about our only set of eyes for transfer down to BTA. GPM plots to establish trends, right? There's the injective performance plots that we use just about all the time. For things like gold, it's also important to know, and for that matter, for any species really, right? What are the nominal efficiencies, right? Remember, the stripping foil, there were those two lobes on the side, and unless you're going to change the properties of the materials in the foil, right, there's an upper limit to how much you can actually transport down BTA. For gold, it's typically about 2/3, actually. So there is an upper limit to how much you can transport. And for protons, it's generally limited. BTA transport could be 100, and then AGS injection is awful because of the snakes. Right, so, and a lot of these overlap with the earlier talks. You have the current transformers in both machines. Remember, the current transformers are relatively slow, right? Millisecond, many turns. You're going to need many turns of beam in order to see it there. Very often, you're making it into the AGS, and the comfort display in the current transformers will tell you 0, simply because you haven't accumulated enough turns for them to be useful. But the wall current monitor, assuming you're making it, where's the wall current monitor physically located in the AGS, by the way? 5. So the kicker's at A5, so there's no room for wall current monitor. A15 is the multi-wire. G5. Right, and where is it? How do you look at it? How do you get it on a scope?
Hardwired signal.
Right, it's a hardwired signal from MCR3. And the booster wall current monitor, I don't know what the booster wall current monitor is in the ring.
There's 2 of them.
Right.
And the RF owns one and we own the other, and nobody knows which one is which. So there's one at A6 and there's one at E6.
Okay.
So I don't know which one is which.
And the signal, which is sort of more important, where's that? On MCR4, right. That's the signal.
Right.
Where is
our
it?
current muck system, anything faster than a millisecond, we can't get in the muck. Right? So if it's faster than a millisecond when it pulses, it's going to have to be a hardwired signal, otherwise it'll be just distorted. So any kicker, PUEs, wall current monitors are all going to be hardwired.
And the bumps and the stuff that you can all get from crossbar. Right, I just listed the places in the directory. Right, does beam get out of the booster? As I mentioned, right, you can cut off a lot by just looking at 006, right? Are we getting past F6? And then you can start working your way upstream from there. Did we make it to the F3 kick even? The last one, a common problem was the RF dropping out just before actual extraction time, which looks very much like you're extracting properly, right? Because all the beam just goes away in the booster. And you can blame lots of things, so it's important to know what's going on, that you're not even making it to the extraction sticker, right? We simultaneously had problems with F6. So distinguishing those two is a matter of looking on a scope at really millisecond differences. Right? We talked a lot about this transport and VTA. If things are bad, you're going to want to check the booster extraction VTA page for tripped elements. The alarm display will tell you about tripped elements. It won't tell you about elements that are, it won't necessarily tell you about elements that are wandering around far from their set point. And very often, I run very often multiple quads will trip, and that's sometimes better than actually having one off for that reason.
If you lose one, you're done. If you lose actually 2 in a row, it's going to be ugly and big. But remember that, so you're going out, the one is off, you keep going out, but when you hit that second one, normally you would really diverge. But without that guy there, you just keep getting fatter. So you can often, if they die in pairs, you can survive.
Right, and so BTA being a transport line sort of lends itself to a nice systematic approach. Like going to the beginning, do I make it to the end, and then you can slowly narrow your way down. And then there's the issue of whether magnets have tripped recently, right? They could be following their set points just fine, but the big bends in particular, everything starts at D8, right? 1, 2, and 3, 4, and 5. They've tripped recently, right? There are hysteresis effects that you really have to pay attention to. So the same, just being at the same current isn't necessarily going to get you the same field.
Right, DH4 is especially bad.
Right,
DH4,
right.
when you turn it off for Lotto and turn it back on, often the set point changes by 10 amps. It goes from 45 to 55. I don't know why it's quantized, but you come back on, it'll be 55. The next time you turn it off, you'll come back on, it'll be 45. So it's a very simple thing to check. Just try change it by 10 amps and see if you see it on the next multiplier.
And if you had a bad mode switch, right, if something happened during a mode switch that caused you to do something out of sequence or something like this, then you certainly going to want to check, because all the set points will match all the readbacks, but whether they're for your species or whether you followed the hysteresis loop that we've been using for the whole run is more difficult to tell. But you can check all the set points and readbacks in log view, right, if you want to see what a good mode switch looks like, for instance. You can also see if when the magnet tripped and how it was brought back on. Again, we talked about this a little bit. So does the beam get into the AGS? Not a lot of things can tell you this. There's 166 to tell you you've gotten near the end of the VTA, but like I said, there are a few quads and DH5 between you and actual AGS injection. The Wolfram monitor is a fast device that can see as little as one turn, know how many transfers you're getting from the booster, how many punches per transfer. The injection current. Yes, I should. Right. So the A15 multi-wire is really the first thing in the AGS that will tell you. I don't think there's even a pickup before that. And then it's a long way to G5. But there are hardwired pickup signals also available. Incidentally, the tune meter, if you're making it to the tune meter pickup, you can trigger on the tune meter application, and I just saw this now. You can trigger on the booster extraction trigger that will show you injection oscillations in a way similar to Rick injection, assuming you're making it to that pickup.
What do you trigger on?
I would trigger on the F3A5 trigger. So there's a scope trigger that comes out with F3A5, which trigger on the same. They always trigger together. You're cool with that?
Yeah, you can do that in the application.
I don't know if it's an easy option. I want to make it an easy option. But they were doing it for the polarized proton setup pretty routinely. AGS loss monitors do not see beam in injection. I say generally insensitive. I've never seen any beam loss in injection, ever. Right, we've talked about this once. They're under the girder, right, so the main magnets sit up on those big girders, and then there are long coax cables under the girder, so that they're all approximately equally shielded, because some AGS main magnets have their back legs out and some of them have them in. And so to make the amount of shielding between them very large for everybody, these guys are under a girder. So low energy beam is just not going to make it out. You're not going to see you're not going to be able to diagnose beam loss in the AGS at injection with the loss monitors, sadly. So if you see things, if you see, say, many turns in the AGS, but they, on the wall current monitor, for instance, the amplitude is successively decaying away, you can check pretty much all the things that you would have checked for booster injection. It's a similar rundown, right? Are the injection bumps on? Are they triggering at the correct time? Are they going away too quickly? It's unlikely. More likely, the amplitudes need to be changed, particularly for polarized protons. The orbit at AGS injection for polarized protons is very sensitive. And so there's a lot of L20 position angle tweaking and L20 septum amplitude tweaking. But almost anything you can do with the septum, you can do with position angle for polarized protons. The dwell field is typically a setup issue or a post-maintenance issue, but that can be checked. If the log view is set up properly, there's a reading for that in log view. I have to add this. Leaf has very nice measurements of the energy. So if there's beam, well, as a function of main magnet, which is very nice, and I think for like the whole cycle under AGS polarized protons in log view. So you're usually at the mercy of like the V-bar, which is appalling and only shows you the last hour or something. Anyhow, you can check the AGS dwell field. Are the tunes and chromes where they ought to be? More of an issue for polarized protons than for gold, which is a little bit more forgiving. Transition quad, if transition timing is somehow horribly hosed, right? You want to make sure that there's nothing that shouldn't be on injection. This is mostly a setup issue. Extraction equipment is the same way. Are we trying to extract as soon as the beam gets in? It's less common than some of the other issues. You have the orbit correctors available to you in the AGS. I talked about them more in the acceleration, so they're more useful during the acceleration phase. We talked about the 820 multi-wire. And the snakes are important. I'll talk about the snakes more again in the next talk, but are they on and should they be on? Remember, for polarized protons, we have these monster magnets that distort the lattice quite handily. And when we're switching between gold and protons, it's imperative that these things are in the state you would like them to be in. The warm snake is usually the one that we leave on or off, and it takes forever to find for some reason. It's easy enough to find in the pet page. It's exactly where AGS polarized protons, but for some reason we are apt to forget. Similarly, there's a sorry?
No, 100 amps in the warm snake will not allow gold injection. So if we're bouncing back and forth, I think that was one of the things I would break on people. I try and break things that are like realistic in what we're doing. And when we're going back and forth all the time, these things are getting ramped up, ramped down. It's not TPM, it stays on all the time. So if the set point doesn't take from tape, we can get stuck on. So if the snake is on, you're done.
Similarly, because they represent such a large distortion to the lattice, they have all these quadrupoles and orbit bumps that go with them, and you want to make sure that those are ppm. And so those are usually less of a problem because on the gold user, on the non-proton users, the function is typically 0, but typically. These are relatively rare. The IPM actually puts a kick on the beam. This is high voltage. We have a corrector for that, but it is correcting for the IPM being on. So if the IPM is suddenly off, usually we tune up protons for the IPM to be on all the time, and gold for it to be off in normal operation because it doesn't harm protons the way it harms gold. That hasn't been an issue lately. That gets taken care of in the mode switch usually, but it's something to check. Right. All right. So in addition to the kick from the high voltage, there's a leak. So for protons, okay. So does everybody know how an IPM works? The beam travels through the beam pipe, interacts with the gas, and ionizes some of the residual gas. And there's high voltage to drag the ions in one direction, the newly ionized gas atoms in one direction, and the electrons from that ionization in the other direction. We measure, in the AGS, we measure the ions. We measure the profile of the ions, and calculate from that what the beam profile looks like. So this high voltage kick is not insignificant. It puts an orbit kick on the beam, and so in AGS orbit control, we put in a bumps compensate for it. In addition, you need residual gas to get a reasonable measurement. For gold, it's not an issue. It's the interaction cross-section is large enough that we get plenty of signal for gold with no leak. You turn the leak on for gold, it starts to capture the electrons, the gold, 77, huge charge, right? Starts to capture electrons. The charge state goes down, and then we lose that beam, right? It does not circulate. It's just like having a vacuum leak, because that's what it is, right? It's just a new valve that we leak into. For protons, it's not an issue, and so for protons, it's on all the time. For gold, it's never on, unless we're actively using the IPM, and even then, we usually don't need it, unless it's low intensity. So you want to make sure that it's in the right state for whatever it is that you're doing. And it takes time, right? When we switch back from polarized protons to gold, it takes time for this leak to pump down, right? The pressure will increase. So you might see the efficiency creep up over time. So like I said, that was, you can think about this. Typically, you can divide, when you're troubleshooting, you can divide the problem into one of four areas, and then zoom in on any one of those four.
I had trouble determining how many transfers got into the AGS during that the 85 and AGS welfare monitor. I couldn't really tell if there was one or four or what.
Well, the important thing to note is the harmonic, right? So for gold, the harmonic in the booster is 6, and there are 4 booster pulses. So how many bunches result in the AGS then after all 4? 24, right? So one transfer from the booster should have 6 bunches in it. And so how many do you see there?
Well, I thought that was one.
Right, that is one transfer. And then if you measure that distance, there should be 3 empty transfers, and then you're seeing a second turn.
So that's one transfer
And 2 turns. Right, with 6 bunches in each turn.
So that's what I said earlier, one transfer, and I thought the answer was 2.
The answer was 2 turns.
The answer was 2 turns.
Right.
Okay.
One transfer with 6 bunches in it, and then you see them come around again later.
So with the protons now, you were showing all of the transfers? There was another picture.
Right, so for protons, how many booster transfers are there per AGS cycle?
One.
One. And how many bunches in the transfer?
One.
One. Right, so there'll be nothing in the AGS, just like the yellow trace here, right? There'll be nothing, and then there will be one equally spaced at the revolution period. You'll just get 1, 1, 1. I don't know. Or was there another one? Yes.
Right, so if this were protons, and the revolution period were the same, which is you would see, if there's 2 turns, and this is protons, you'd only see 2 spikes, right? If there's 2, we're looking at 2 turns in the AGS, 1 bunch per turn, so it'd be spike, gap, spike. So that's the important thing to know. You need to know which transfer you're looking at, how many transfers there are, and how many bunches in each transfer.
Right, this can only be the next turn in the AGS because this is 2 microseconds long. Right, the next load from the booster doesn't come for a long, long time on this scale, right? So all the bunches, all 6 bunches in the booster leave. They fill up a quarter of the AGS ring, and then the booster ramp is now ramping back down, and the AGS beam is just circulating and comes around again. And so the next time I'm going to put 6 more bunches here, and we'll see them again here, and then again.
Initially, when I said 1 transfer, I thought someone said 2, and I thought that was inferred to be the right answer. But this is really 1 transfer. So,
Right.
So I really had the right understanding the first time. Okay. I changed my whole understanding.
Okay, so Mike thought everything you just learned was
Glad we cleared that up. The RPM. So there are just two plates here, right? At some voltage with respect to one another. So there's an electric field from one plate to the other, right? That's meant to drag these ionized bits into the detectors, which are all specific configuration. So when the beam comes by, it sees this and just gets a kick. right? The same way as if I had put a steering dipole here. Right, so instead of if the orbit had previously been flat, I now get what looks like Vincent, right, with a cusp at the location of the IPM.
So it will vibrate along the different orbits.
Right. So if I take an orbit with the IPM off, no voltage, right, and take a difference orbit, then turn it on, and take a difference orbit, I see something like this, right? And that can affect transmission efficiency, right, because the orbit isn't the same on and off.
So for if the species is proton, we use it, right, to get emission. Or if the species is ion, do we use it?
The voltage, if you want an IPM profile, the voltage has to be on. It's the leak that is different for the two species.
Yeah, if the leak is correct, the parameter is set up correctly.
Right.
Will the on and off matter?
Yes. The electric field is independent of the vacuum state, right? Whether I'm leaking vacuum into here or not doesn't make a difference, right? It's just about whether this voltage is on or off.
Right, but when you're on, for protons, we leave the high voltage on. Now, put in the correction. So we correct this with a kick later.
Oh, it's the
Right.
kick. Oh.
There's a, what do you have, a single
It's
dipole?
there's a single dipole.
Right, so somewhere down there's a single dipole that gets rid of this.
Probably E.
And usually we don't touch that, right? So the dipole and everything.
Right, it's set up to expect to have the dipole on and the high voltage on for proton. So it'll only oscillate for a tiny bit before it gets flattened back out.
So the RPM should always on, the high voltage for RPM should be always on, right?
For proton.
For
For
proton.
proton.
And off
Is that the phase that it's at?
for
For
gold.
one
For gold.
being
Almost certainly not.
No, yeah.
Okay.
Right, because it is E15, right? So I think, you don't even go through a quarter of the,
Right.
yeah, so.
Yeah.
The quarter.
Oh.
The next corrector downstream is not necessarily the one that we use, but it's the one I would start with. I'm not sure which corrector we use, but it's just thing above.
So we don't use RPM to measure the. For
We
gold.
don't use the IPM to
But how do you get
how you get admittance.
Right, I
You're
just
saying how many correctors is it? Three?
Oh, there.
Three away?
Oh, that.
three main magnets.
E15? Where is it?
E15
The E is
is the next corrector. You don't have to use the one downstream if you want to.
Wouldn't that complicate things?
It will, but you could use it.
What are you saying, leave it on for gold?
You could leave it on gold and just have different settings.
Yeah, but we don't ever use the IPM for gold, so that's the thing.
Right.
That's why it's not.
And the parameter for gold is 0 or 1200.
I'm guessing it's 0 if we went
Zero,
on
right?
the job.
Or if the high voltage is off, it doesn't matter, right? That leak parameter doesn't matter.
No. There's two separate things. So the high voltage
Yeah.
creates the distortion.
Yeah.
The leak ruins the vacuum.
Mm.
For gold, the leak should be off all the time because the vacuum is poor enough that you get some ions coming off all the time anyway.
So the parameter is 0 for gold.
The leak parameter.
Yeah.
Yes.
Okay. And you say the parameter is separate from the high voltage on and off.
The leak setting is different from the high voltage on and off.
Yeah. And then no matter your high voltage on or off, the leak parameter should be always 0. Like your high voltage is off. Can you use a set of parameter, the leak parameter to like 100?
Can you? Yes. Would you want to? No.
Okay, so
You're going to ruin the vacuum and get nothing out of it.
Yeah. Okay.
Right. So it can be screwed up.
Can
And
be screwed
tape
up.
sends
Okay.
the value. Sometimes the tape command doesn't always get picked up.
It's not like if you shut off the high voltage.
Oh, the
it
leak
will-
automatically goes away.
No.
Two separate
Okay.
things. Mechanical valves and power supply.
And you're gonna see the injection, the beam will inject and die.
With the leak on,
Yeah,
Yeah.
it's not going to be violent. It's just
No.
not going to be very efficient.
vacuum problems in the AGS usually look like
Yeah,
this.
they're kind of subtle because the vacuum in the AGS isn't all that great to start with. Right,
This is a bad one.
Right,
Like
that-
this is what it looked like when we blew a hole in the pipe. This is bad.
It
Right.
looks like that.
There's just this
That's
constant.
bad. Yeah, the constant beam loss around every.
And the high voltage.
The leak would be somewhat more subtle.
If this is like if you the lead parameters, well, how about you turn on the high voltage? If this goes, how about you turn on the high voltage for RPM?
The lifetime is probably okay. It's probably like injection efficiency that gets worse. So rather than be up here, you would, for instance,
Because the orbit is screwed up.
the orbit is messed up. It looks like you should spin the orbit.
So the RPM, if RPM is on, you will still have to get in, but the efficiency will be much lower.
Yeah, the IPM doesn't destroy the boom. It doesn't kill it altogether. It's not that strong. It just makes things, it makes the efficiency. Usually the transfer.
But that's a good question. I mean, when you take these exams, you should have a list of things in your head that will kill you. Like, you see being late in the booster, you see no beam in AGS injection. Where do you go first? No. You see beam late in the booster and nothing in the AGS. What do you check first? Right. Put in 6. Right. You're not getting to 6. What power supplies can screw you up? What power supply is in your head? You're not getting to 6. Right? Which is bumps, F3 and F6. Check and make sure they're all enough to set point. You're getting to F6, or you're getting to 006. You're not getting to 60. What's a good thing to check? Dripping foil, DH2 and 3, big bend, lots of power, right? If it's off, that's screw you up. You're getting to 60, not to 125 or 166. Quads, DH4, right? You're in 166 and you're not getting circulating beam in the AGS. You don't see anything on A15. You put A15 in. You think everything's good, but you don't see anything on A15. This thing, well, L20. Anything else? Will, you should have a really good answer to this.
Injection bumps?
No? Injection field. If you think that you're getting through L20 and A5 and you got all that stuff on, and you're not making it through 10 dipoles, the only thing that can kill you in that distance is the dual field approach. Okay? If you get to A15 and you're not circulating, then it becomes more subtle. Right? Then you're looking for somebody left at heat run function skew cluster. Vincent and I took us 20 minutes to find out what I thought. Okay, but those are the kind of things. Have an idea in your head. Break things down into steps and know what things fail. Honestly, this is the easiest test to take for me because there's 2 pet pages involved. I will not let you use the buffers because all you're going to do is load a buffer and you look for yellow and send yellow. That's way too simple. I want some thinking involved. Okay.
Could you show us the signature for the Woody flux being left on?
Yeah. So I was going to talk more about the polarized proton stuff. So there are these pulse quads at I5 and J5 that we're using to improve the polarization of the AGS, right? That should never ever happen.
Improve in quotes. Right now, because it doesn't actually work.
So this is a polarized proton cycle, okay? And the quads are on pulse madly 82 times between here and something like that, right? So their functions look like this. Because the jump, the effect on the beam has to be the same, so the current goes up and up with and then, I don't know what this spacing is, but it happens 82 times between here and there, okay? And they blow up the emittance of the proton beam, and like I said, I'll talk about the usual deleterious effects. This, on the other hand, is a gold cycle. Right? The injection porch is longer because we have 4 transfers as opposed to the 1, right? So what this looks like, so they're only good for polarized protons, right? Let's just be perfectly clear. They're only good for addition. There's no reason in the universe they should be on for heavy ion. So what the injection transformer should look like for gold is, oh right, this is 0. Right? So this is beam on the gold cycle, right? If if these quads happen to be on for the gold cycle, what you'll see instead is this very strange in, nothing, in, accelerate. Because they only ruin you for the length of the polarized proton cycle, which happens to coincide with transfers 2 and 3 from the booster. So there's this goofy thing where if somebody leaves Woody's quads on on the gold cycle, the transfers look beautiful because they're just off for this period of time. They're just not there, and then they go away again for the 4th transfer. This was just nice because the comfort display looks like you have never seen it before. And it doesn't make any sense, right? So we're looking at pulse power. Incidentally, we started with the pulse power, right? Because it's the only real thing that's going to mess you up that quickly and just go away like that, right? So we were looking at F6 and F3, A5 because at some point somebody vouched for jump quad. And I should just say, since we're here, the jump quads have a GPM that you can look at. That'll show you what the turns on.
Okay, last questions.
Yeah, I want to go back to the scope picture that we had with the Walker monitors. Like, I was understanding what you were saying on the left-hand side is the first extraction for Rick, but it kind of confused
First
me.
extraction for Rick?
Right, wasn't that?
How does, yeah, can you pull this real quick? I mean, so we're talking about boost and AGS.
Right.
What do
So
you mean first
the
extraction?
AGS extraction, AGS Walker monitor had the first 2 turns of the first cycle. What was on the left-hand side?
So what are we
I
talking
kinda
about?
confused myself. The red drawing on the
This
left-hand
picture?
side. Yeah.
Oh, okay.
Oh, so this is time 0 with respect to a certain transfer from the booster.
Right.
If you're looking at something other than, so let's say you're looking at cycle 3. So there's already been one group of 6 put into the AGS.
Right.
That group of 6 stays as a group of 6, takes up a quarter of the ring, and it just keeps swirling while the booster does its thing. So when this scope trigger gets, when it happens on the next cycle, there will be 6 bunches on the left. And then once you inject 6 new ones, there will be now 2 groups of 6, or 12, a group of 12 and a gap.
Right. So what was the thing with the 18 and then the gap there? That was kind of
That's one cycle later.
That's one cycle later. Right. So what he drew is 18 circulating with one little space.
Right.
And then when the next 6 come in, it will be continuous because that would have to be coming. That would have to be the 5th transfer, the 5th cycle, the 4th transfer.
So right. So this is with the red drawing in there. That's the 4th. That's the 3rd cycle.
With the red drawing in no. If the red drawing has 18 bunches, and then on the right it's continuous with bunches, that would be the 5th cycle or the 4th transfer.
4th transfer. I'm sorry, I mixed that up. Okay.
And it's easy to get screwed up. And we talk about, somebody will say cycle, and when they really mean transfer, because we always just ignore the dummy cycle. Right? So it is easy to get screwed up in the head.
We spent some time once trying to figure out what could kill you after 6 turns. Because we were looking at a picture like that, which was much zoomed in, right? So we were only looking at this, and we were like, what comes up after 6? Like 6 perfect turns and then nothing, right? And you can get screwed up until we realized that the scale was so small that this is much less than an AGS revolution period, and so it's really possible.
So looking at this then, you'll notice A5 is just barely big enough to get those 6 bunches in, right? It's just wide enough. If I move on you for your test, if I move the F3 A5 kicker, I slide it to the left, a couple microseconds. What will you see in the AGS?
4, 3,
Right.
less transfer.
Less transfer, right? And I think almost everybody that I've done this to, I showed you after we were done. If I push it far enough, A5 is just not timed in right, and you'll see nothing. And then you start to walk it, and then magically, whoop, 1 bunch, and then you'll see 2, and then 3, and then when you get back, you'll see 6. It doesn't give you a lot of error, because it just barely fits in there. So F3, A5 is a very sensitive knob, a microsecond delay.
Because A5 does have to go away, right? A5 has to go away. Not like the injection pump, but A5 has got to be gone when the beam comes back around. F3 is less of an issue because all the beams gone around.
When you get to the 4th,
Right, exactly.